All right. Well, today I want to talk about waves. As you may have recognized, I kind of like physics, and waves can be simulated by making a chain of masses, each with some particular mass, connected to each other by springs. And if we look then at one individual mass, the forces acting on it are the spring to the left pulling it one way and the spring to the right pulling it the other way. And so those are the two forces, F equals ma, and we have our second order differential equation. Acceleration is rate of change of velocity, which is rate of change of position. So it's second derivative of position. Now, the other thing to recognize is this right-hand side looks like a central difference approximation of a second derivative. So this stuff over here is delta x squared times the second derivative of u with respect to x. And this actually turns out to be something called the wave equation, where this stuff in front of the second derivative with respect to x is the velocity squared of a wave that travels along this chain of masses. Now, I can solve this using numerical machinery for integrating second order differential equations. What I recognize is that the second derivative of u with respect to time is the acceleration, but acceleration is rate of change of velocity and velocity is rate of change of position. So a second order differential equation is equivalent to two coupled first order equations. And first order equations are easy to solve. The Euler method drops the limit of delta t as delta t goes to 0 from the definition of the derivative. And we end up with two recursion relationships. The new v is the old v plus the acceleration times delta time. The new position is the old position plus the velocity times delta time. A slightly more stable Euler-Kromer method updates the velocity first and then uses that updated velocity to update the position. And we have an even better one, Euler-Richardson, which with our little chain here, masses 0 through L, where 0 and L are considered to be fixed. So we're only going to update position 1 and position L minus 1. I calculate my acceleration, move forward a half step, half of a delta t step. This gives me my velocity and position at the midpoint, which I can then reevaluate that acceleration at, and then do a whole step using that midpoint velocity and position. So that's Euler-Richardson. I'm not going to go through how to get the analytic solution. The important thing to see when we get done here is that I have a solution that has this thing called the wave number in it, Q. And the wave number is an integer. We sometimes refer to this as its normal mode. We have first, second, third normal modes. And these just look like this. It's a solution, a sine that has 1/2 cycle of the sine. That's the first mode. The second mode has a full cycle of the sine. That's the red curve. And as we go to higher and higher modes, we have more and more wiggles as we progress up. And these are the analytic solutions of the wave equation with the particular boundary conditions that the two endpoints are fixed. They're sometimes called standing waves, as you'll see in a minute. They look like this. So the WaveMaker script has the length of the rope, how many points we're going to divide it into. We're going to use a line renderer to display it. We have arrays of our position, displacement, velocities, accelerations, and the analogous properties at the midpoint. We add a component line renderer to our object, set vertex count, width, and color, or material, and assign these uh, the line positions, the various positions of my starting condition. And then, sorry, I turn it over to animate. I turn it over to animate a coroutine that is going to update velocities and positions. By the way, the initialization here, I'm starting off with a particular mode here. So I'm choosing actually a number of modes that I'll add together to give the initial shape of things. And animate is really nothing more than that Euler-Richardson method, updating the positions and velocities. And then assigning those positions that I've updated to my line position. So let me show you what this looks like. First of all, I have a little program here that uh, drives these things. And let me turn on damping so that it settles down here to stop. And I'm going to turn on the slow motion. And now I'm going to turn off the damping and turn back on the driving. And what you'll see is a wave that progresses from the left to the right. It's being driven by this little movement right here. This is what's driving it. And when the wave reaches the other end, it bounces off the other end and travels back. And as you have these two waves going opposite directions through this string, it ends up looking like this standing wave that in this case is mode number 6. And so it has 6 peaks. And if I let it run fast, it does other things. This little program lets you change the frequency. You can switch modes, and it has this damping and driving toggle that you can turn on and off. Here's a comparison of the analytic solution with the transient solution that we're able to do numerically. And the top here is the analytic solution, and below here is the one that's being driven by this little wiggling node here. And they do behave exactly the same way. The analytic solution can't do transients. It's a steady state solution. And here's a case. Here's a case with mode 3 and mode 11 superimposed on each other. So we have the 3 mode, which has kind of 2 stationary points, 3 half sine waves, and then superimposed on that is the higher frequency 11th mode. And here's one just to demonstrate that Unity's physics is pretty good. Instead of applying the forces myself, I used the add force to move the little objects around. So that's waves. I'm going to stop sharing here at this point, and I'm going to end the recording. Next time I'm going to come back and do this in 2 dimensions and make some surfaces that wiggle around. So I'll stop recording. See you in class. Bye.